So, I get the feeling that people are feeling a little out of their depth, and I want to step back a little bit and do something maybe a little more fun and not so much programming. I found this machine learning crash course by Google, and it has some fun exercises. And here, let me get you the link. I think it's just up to here, machine learning crash course like this. Let's see how this works. And I'll give you the link. Yeah, all right, so this is what the page looks like. And I'll put this link in the assignment. So we will do stuff from here. So this will be in your Canvas, so you can refer to this when you need to. All right. Now, if you look at this course, to start crash course here. I don't know why that's there. All right. So you can see on the left-hand side a lot of different stuff. First of all, before you start, please create a profile. The first thing you do is create a profile. So that will be here. So first, create a profile. And the way you do that is, I believe it's up here on the 3 dots, and you go to profile. And I think you need a Gmail or something like that. I hope everybody has Gmail. All right, so here I'll just say 3 dots on the upper right. Because this will give a record of what you've done. And I want to, so if you look here at the different topics, first was linear regression, right, that you're experts in. Then is logistic regression, which you're also experts in, classification, and then working with numerical data. So I don't think it's bad for us to go back over this a little bit. What I want to do is to get up to neural networks. I want to do these, I want to get up to these 3, because this, I feel you're sort of shaky on this. And embeddings we haven't talked about yet, but it's kind of a new innovation, which turns out to be very useful. Now, so we'll be going through these modules, and the times here, well, since we've been over linear regression and logistic regression before, and classification, I want to compress the times here. So I'll kind of give you a tour of these here and have you do a couple of exercises from this one, and this one. And also, I think it's probably useful to work through these also. So these are all topics that we've touched on and probably have covered maybe more than 50% of the material in this. But it's not bad to go back and look over things and reinforce what you've learned already, as long as it's not too boring. All right, so let's go to linear regression here. So so first I'll say, so in a linear regression, linear regression, I don't think you need to go to look at this here. Well, we'll take a quick look now, but I think we can just survey this. This is all very much what you've done before. Is that big enough? Okay. So you know what linear regression is. In this case, they have one feature and one target, and then they plot these, and you want to make a linear model, right? Something like this. So you know that already. And you know this type of equation, right? Where this is the target, this is the feature, and you have 2 coefficients that we've been calling thetas. So it's the same thing, right? And then he calls this one theta 0, he's calling the bias, which is what we did we called that in neural networks as well. And then he calls this a weight. That's also the terminology we use in neural networks. Okay. So he's got this, and the bias and the weight, the theta 0 and theta 1, you calculate from basically a training process. You use your data, and that's what we use for steepest descent. Okay. So all right. Then he has multiple features, which we've done already. Same thing. This is theta 0, theta 1, theta 2, etc. We're just using different letters for the same thing. So this is all very much reviewed. And you can see you fit lines and stuff. So we can pass through this. And I think that's all that we need to. Well, here, can you answer this question? Is that big enough? I don't know why it doesn't get bigger. Here. Okay, there. So what do you think? Which parts of the linear regression equation are updated during the training? Okay, bias and weights. Okay. Yes, so that's right. How about the other ones? Do you update the feature values? No, that's your data. You can't change your data. And the prediction, well, you can't change that either. All right, good. So we've finished linear regression. We finished this part here. Loss we've talked about as well. Right. Loss we use as the square of the sum of squares of deviations. So here's this picture that I showed before. Right. You want to make these deviations small, and so you can do L1 loss, which we are not doing. We're actually doing, and mean absolute error is the same thing. You just multiply by 1 over n. L2 loss is what we're doing. Well, mean squared error is the same thing as L2 loss. It's the same thing. You just divide by 1 over n. So if this is small, then this will be small. So those are the different types of loss. And then, so here he gives an example of calculating loss. And choosing a loss, we can pass by that. Basically, I don't know if you've seen this in other statistics courses, but the mean squared loss is more sensitive to outliers. So in some ways, it's worse. But theoretically, this mean squared loss has some theoretical advantages. All right, so let's look at this one here. Check your understanding. Which one has the higher mean squared error? Well, it's not really clear, is it? Actually, it is. It is, because this one here, this here is 1, a deviation of 1. This one's a deviation of 1. This one's a deviation of 1, and this one's a deviation of 1. This is a deviation of 2, and this is a deviation of 2. So if we were going to calculate the mean squared error, you have 1, 2, 3, 4, 5, 6, 7, 8. You have 10 data points. If we're going to calculate the mean squared error, what would it be? I think we can just do this verbally. What's the squared error here? What's the squared error here? 1, 0, 1, 0, 1, 0, 1, 0. So if you take the sum of the squared errors, what do you get? 4. Okay. So what's the mean squared error? Well, the mean squared error is you take the sum of the squared errors and divide by the number of data points. Well, no, you're squaring the error again. You've got the squared error. Why do you square it again? Right? 4 over 10. 4 over 10. Okay. Now, how about this one? This one has 1, 2, well, this only has 1, 2, 3, 4, 5, 6, 7, 8 data points. This one has squared error 0, 0, 0. What's the squared error here? Nope. Squared error. Yeah, the squared error is 4. The error is, see, I guess I wasn't following how you're computing here. Here the error is 1, and the squared error is also 1. Here the error is 2, the squared error is 4. Okay, and this one here, also 4. Okay, so what's the mean squared error over here? Well, what's the sum of squared errors? Yes, divide by 8. Very good, so it's 1. Okay, so which one has bigger mean squared error? This one. Okay. All right, so as I said, these are outliers, right? So mean squared error is more sensitive to outliers. Now, if you're going to do mean average error or mean absolute error, you get a different story. We can compute that too. What's the mean absolute error here? It's the same, right? Because when you square 1, you get 1. Okay. So this has, so mean absolute error is going to be 4/10. And what's the mean absolute error here? So in this case, you have 8 data points, right? And the sum of absolute errors is 4. All right, so it's still bigger. But so this one was 0.4, this was 0.5, but they're a lot closer. Now they're a lot closer. Before they were quite different. This was 0.4, this was 1. So that shows that mean squared error is more sensitive to outliers. All right, so we're done with that. Okay, so interactive exercise. This one's kind of fun. So what I'm going to ask you to do is do the interactive exercise, and I'd like you to take a screenshot and put it into a Word document. Take a screenshot of your final result and put it into a Word document. So you're going to submit the Word document to me. Okay? So this is linear regression, interactive exercise. Where's my page? Linear regression, interactive exercise. So here, all right, so here I'm going to say create a Word document. That you will paste screenshots into. Okay. So interactive exercise. Okay, and then here I want you to paste one screenshot of your solution. Now, according to this will take 5 minutes. So I'm going to. This is the wrong one. This is the right one. So that should take something like 5 minutes. And because, yeah, I think that's reasonable. So we'll just say that's. So I want to estimate how much time we're going to take to do all this stuff. So now we go to the next one here, gradient descent. So we've talked about this before, so we'll go through this briefly. There may be a few new things here. So there's a video. I don't think you need to watch the video because we've talked about this quite a bit. And here, basically, the procedure is you see, calculate the loss, determine the direction where the loss will decrease, move in that direction, and then repeat the process. So that's just the same thing we've been doing before. Okay. And there's a diagram, blah, blah, blah. It says, and we don't need to do that. And we have a loss curve. We've seen loss curves before. You made a loss curve. So this is what happens to the loss as the iterations increase. Okay. So, all right, let's see. I'm not sure what this is about. All right, so this says at the beginning that he chose a very bad value at the beginning. That's why the point here is so high. And then right away it gets a lot better very quickly. So this is really bad. Then as you iterate, the slope and the intercept will adjust to fit the data. So let's see. Now I don't know why it's like this. Why doesn't it have a slope? Oh well, never mind. Okay, so I'm not sure. Okay. All right, so just to let's see, how many answers are there here? Just to make sure that you're awake and functioning fairly coherently, let's do this question. What's the role of gradient descent in linear regression? What do you think? Which one? Okay. Are you sure? You think. You think, therefore you are. Okay. What do you think? Okay, what do you think? Okay, I think you're right. Okay, so that's correct. Okay, so correct answer. Okay. We also talked about convex functions, that in this case our loss function does have a unique minimum. So this is all review. We don't have to talk about this. And we talked about how the gradient descent follows the valley to get to the lowest point. So this is all stuff that we saw before. All right, good. So we passed this by. Hyperparameters. This is something that we didn't quite talk about. But it's not difficult. We did talk about learning rate. Right? That was the alpha. And alpha is too big, it may jump around. Alpha too small, it will take a long time to get there. Batch size, we didn't talk about this. Now, he's talking about, well, here, let's go and see. So I can skip over learning rate. You know all about that stuff. Yeah, here's a case where it's jumping around too much because the learning rate is too big. It's like the kid when you tell him something and he says, "Oh yes, I understand." He doesn't really understand. He just thinks he understands. Okay. All right. So, all right, batch size. Now he's looking at a case where you don't update your coefficients each time. What you do is you take let's see how. Oh, okay. Sorry. So no, he's looking at a case where you have lots and lots and lots of data, and you don't use all the data at once. You use some of the data to do your update, and then you use more data to make another update. So that's called a batch. You don't use all of your data to update your estimate. And generally in linear regression, you don't use batches. But in neural networks, you do use batches. So that's why he's introducing it. So that's what batch size means. It's something we haven't seen before. But the idea is very clear. It's just you don't use all your data, use some of your data, then you make an update, then you use some of your data and make an update. So that's all that batch size. Let's see. So we can pass by this stuff. And then epoch just means how many batches you use. Okay. Sorry, epoch is different. So when you do batches, you'll do one batch at a time, and you'll update for each batch, and then you run through all your data again. And that's called the epoch. So if you run through all of your data once, that's an epoch. And then you run through your data again, that's another epoch. So that's the terminology there. That's just how much is using part of your data. Epoch means how many times you run through all of your data. Now, when we did linear regression, our batch size was basically all of the data at once. We used all the data to compute the gradient, and then we updated. And then our epoch was basically the number of times we updated. So in this case, you basically have two steps. Instead of using all the data to do an update, you take part of the data. All right. Yeah, so here we did full batch an entire data set. So here's a single batch, a mini batch. So one epoch is several mini batches. Okay. All right, now let's see. Do they have a question here? Okay. Okay, when we say stochastic gradient descent, that's what we did. So what's the best batch size? And the answer is pretty clear. What would you answer if you didn't know anything? It depends. Of course it depends. Yes, okay, it depends, yes. So you need more information. All right, so here it says, doubling the learning rate can slow down training, and larger batch sizes are unsuitable for data with many outliers. What do you think? Okay. All right, so why didn't you say the first one? Well, we know what can happen when you double the learning rate. Does doubling the learning rate always make the training faster? No. In fact, it can make it diverge. So I think that's a good answer. The second one, why did you say the second one? Okay. Well, it turns out that if you have outliers, then you want larger batch sizes, so you can average out the outlier. You don't want a small batch for an outlier, because if you have an outlier and your batch happens to contain that outlier, then you're going to go off into outer space. So, as you know in statistics, when you take averages, you reduce the effective outliers. So in fact, the first one is correct, I think. Yes. And the second one is not correct. Okay, so I think we can pass by that because we don't need too much. So interactive exercise. And this one, I think we can do this one. All right, so this is another one where you can just where you just twiddle with stuff. Okay. And here also, so do the interactive exercise and interactive exercise for gradient descent. Where did I put that? Okay. So this was interactive exercise for what? For what? For parameters. So I want this one here, and then I want, and I also want the interactive exercise for gradient descent. And you may need more than one screenshot, so I'll just say screenshots, however many screenshots. And there's also a programming exercise. I think it's a fairly simple programming. Let me take a look here. But you can do the exercise in your browser with Colab. And let's see how complicated this is. Mm-hmm. All right. Well, let's pass this by because I do want to get to neural networks. We might do it later. I'll take a look and see if it's suitable. But I think we've done similar things already. All right. So let's go to logistic regression. Logistic regression. I think here I would go directly to all right, so we can pass through this quickly. I want you to do test your knowledge. If you do test your knowledge, then you earn a badge. Okay, so the point of this is to earn badges. You always want to earn badges. You will do test your knowledge. So let's go here. Down here? Yes, okay. I don't think I need to do the introduction. Calculating probability, I think they use so calculating probability with a sigmoid function. This is what we did. You convert an arbitrary real number to a number between 0 and 1. Same function we had before. And you take this model with the bias and the weights, and you apply the sigmoid function, you get a number between 0 and 1. So this should all be familiar. All right, so here, check your understanding. A logistic regression model with 3 features has the following bias and weights. So you have bias and 3 weights. Given the following input values, answer the following 2 questions. What is the value of Z? How would you compute it? Yeah, okay. So how would I compute it? Actually, maybe I can I grab this? No, I cannot. It's not going to let me. All right, so what steps would I take to compute this? Yeah, take B plus x1 times w1 plus x2 times w3 plus w3. So we can do this quickly. That's 1. Then w1 x1 is 0. w2 times x2 is minus 10. w3 times x3 is 10. So his value is 1. Right? Yeah. Yeah, because it did 1 plus 10 minus 10. 1 plus 10 minus 10. Okay, good. All right, now, What is the logistic regression prediction for these these input values? And you don't actually need to compute. You can guess what it is. The value of z is 1. So what do you think the logistic regression function evaluated at 1 is going to be? Can you eliminate any of these choices? It can't be 1. We can eliminate that because that would be certainty. That would be infinity. All right. Okay, 0.5, but we know what 0.5 is. We know what z is for 0.5. What is z for 0.5? It's 0, right? When it's 0, that means you don't know, you're indifferent. You don't know if it's positive or negative. You don't even need to figure that out. If you have a positive value, is that going to have a probability bigger than 0.5 or less than 0.5? Yeah, it's going to have a probability bigger than 0.5. Is that bigger than 0.5?
No. If you said if we have a positive value.
Yes.
For z.
Yes.
Oh, okay.
Right, because 0.5 is the value when you have 0. You don't know if it's positive or negative. If it's positive, it's certainly going to be bigger than 0.5. So, okay, so that's I think everything for logistic. And we talked about loss and regularization, so we can just skim that. I think we know that, we know all that stuff. The loss function is here. We've seen that before, if you don't remember it, right? And then the regularization is L2 regularization. We talked about that. I don't think we need to, well, I can click in there, but that's just going to add something to the loss function. You take this, you take a multiple times the sum of the weights. And hopefully he has the expression down here. All right, yes, it says lambda times complexity. So we had a lambda. It looks like he doesn't have the explicit formula. But this is the same thing. This is the same thing that we did before. So for logistic regression, please just do the, test your knowledge. You should be able to do that. It's just a multiple choice quiz. And you'll earn a badge. Okay. Classification. Okay. So we've done this also. Thresholds and confusion matrix. I think we know all about that. Accuracy, recall, and precision. We know about that. ROC and AUC. We don't need to talk about that. Well, actually we do to test your knowledge. So you can learn about ROC and AUC. So I'll put that on the assignment. So this would be classification. So you do ROC and AUC. And then what else? Prediction bias. I think these are all very small, so it doesn't. We can skip the programming. Then you should, so as a result of this, you should earn a badge. In your profile. I think you missed the first part, which you need to create a profile. Well, it's in the, and this will also, so this will also test your knowledge. All right, so far, what have we done? So far, we have the linear regression, logistic regression, classification. So let's see how far we can get there. I think we should be able to get there. I think we should be able to do that all within an hour. Let's try that. So I will post this assignment so that you have a guideline, and I'll make this it's a Google Crash Course Part 1, and we'll make it due today because we're going to finish this today. I don't think it's 10 points. We'll make it 5 points. And the online submission, file upload, unlimited. This is not a group assignment. Graders can assign it, and we'll make it due today. Today is what? Tuesday. All right, so we'll do that. And I'll put 11:59, but we should be able to finish it this morning. And here it is. And all right, there it is. So the description of what to do is right there. And I'll stop recording.